Welcome to this third presentation about the best methods to convert aldehydes into alkenes. This presentation is about the condensation of aldehydes with the most common carbon nucleophiles, for instance the enolates of ketones, carboxylic acid derivatives or nitroalkanes. This is an important group of carbon-carbon bond-forming reactions that is well suited for large-scale preparations because only water is formed as byproduct. Condensations under basic reaction conditions proceed as sketched here. The anionic nucleophile adds to the aldehyde carbonyl group and the initially formed secondary alcohol eliminates hydroxide or water. Such condensations can succeed even if the aldehyde is much more acidic than the protonated nucleophile because in aprotic solvents the addition to an aldehyde can be much faster than its deprotonation. Under acidic conditions, the aldehyde or its protonated form attack the enolized nucleophile, as sketched here. Elimination of water again yields the final condensation product. Ketones and most carboxylic acid derivatives are less acidic than aldehydes, but directed condensations with preformed enolates can succeed anyway, despite large pKa differences, because enolate formation in aprotic solvents is a slow reaction. Nonetheless, condensations of very basic, sterically demanding nucleophiles, such as metallated amides, with enolizable aldehydes might not work at all, because of a fast deprotonation of the aldehyde by the nucleophile. Enolizable aldehydes undergo aldol additions and condensations already during storage, and their quality should therefore be checked before use. One way to accelerate such condensations is by adding ammonium carboxylates, as in this example. Here, a catalytic amount of pyrrolidine and benzoic acid led to a complete condensation within 14 hours at room temperature. It is sometimes even possible to perform cross-condensations between two different aldehydes. In this example, acrolein was used as a synthetic equivalent of 3-iodopropanol, and the condensation was brought about by an excess of titanium tetrachloride. A better strategy for directed cross-condensations of two different aldehydes is the stoichiometric metallation of an imine followed by addition of an aldehyde. Imines are less acidic than aldehydes, and metallated imines therefore more basic and nucleophilic than simple aldehyde enolates. Acid-catalyzed hydrolysis then yields the final alpha-beta unsaturated aldehyde. When a ketone is mixed with an aldehyde and a base, the aldehyde usually acts as electrophile and the ketone as nucleophile, as in this example. Here, in order to attain a complete conversion of the starting ketone, a large excess of acetaldehyde had to be added portion-wise within 12 hours, probably because a lot of acetaldehyde was lost by self-condensation. If the reaction conditions are too mild, the initially formed secondary alcohols will not undergo elimination. The olefin can sometimes be obtained by acid-catalyzed dehydration, as in this example, or by treatment with an amine and acetic anhydride, thionyl chloride, or methane sulfonyl chloride. In this example, citronellal was condensed with an excess of acetone. Under these optimized conditions, and despite the excess of acetone, no Michael addition to the product occurred. As catalyst, again an ammonium carboxylate was used. Base-sensitive ketones, as the starting material of this example, can sometimes be cleanly olefinated under slightly acidic conditions. Here, a condensation with formaldehyde succeeded in acetic acid with half an equivalent of morpholine as catalyst. 3-ketoesters are usually olefinated at position 4 by stoichiometric formation of a dianion followed by addition of the electrophile. Sometimes this gamma functionalization is, however, also possible without dianion formation. Here, a ketoester underwent clean condensation at position 4 with only one equivalent of dBu as base. Unfortunately, this reaction only worked well with non-enolizable aldehydes. Alpha-beta unsaturated aldehydes are 1,3-dielectrophiles and can in principle form 6-membered rings upon reaction with ketones. This was accomplished in this example by first condensing acrolein with a ketone under acidic conditions. The intermediate diene then underwent thermal intramolecular Michael addition to yield a substituted cyclohexenone. This here is another example of an acid-catalyzed aldol condensation. Not all starting materials are compatible with these conditions, but if they are, this is one of the most economical ways to prepare enones. The combination of titanium tetrachloride with tertiary amines offers mild conditions for the generation of enolates. In this example, this strategy was used to condense a polycyclic ketone with an excess of acetaldehyde. When carboxylic esters are lithiated with LDA and an aldehyde is added at low temperature, aqueous workup usually yields secondary alcohols. Single-step olefinations of aldehydes with carboxylic esters are, however, possible at higher reaction temperatures, as in this example. Because during condensations one equivalent of water is formed, this will cause the saponification of most esters. Therefore, here an esterification step had to be added. Lactones are more acidic than open-chain esters. In this example, sodium methoxide was sufficiently basic to mediate condensation of butyrolactone with an aldehyde at room temperature. Carboxylic anhydrides are more acidic than esters and can be used as carbon nucleophiles. In the classical Perkin reaction, aldehydes are condensed with acetic anhydride and sodium or potassium acetate as base, like in this example. Unfortunately, these condensations only give good results with non-enolizable aldehydes. The main products from enolizable aldehydes are enol acetates. An alternative to condensations with acetic anhydride are Knövenagel condensations with malonic acid followed by decarboxylation. With other anhydrides than acetic anhydride, however, direct Perkin-type condensations with enolizable aldehydes are sometimes possible. In this example, phenylacetic acid could be condensed with propanal, but in moderate yield only. This is an example of one-pot oxazolone formation and condensation with an aromatic aldehyde, again with an excess of acetic anhydride and sodium acetate as base. When acylated alpha amino acids are heated with acetic anhydride, oxazolones are formed by cyclodehydration. Oxazolones are still more acidic than butyrolactone because enolization causes oxazolones to become aromatic. Electrophilic attack by the aldehyde of the acetylated oxazolone followed by elimination of acetic acid yielded here the observed product. One potential side reaction of the activation of carboxylic acids with acetic anhydride is the Dakin-West reaction. This occurs when the oxazolone or another activated acid derivative is acetylated at carbon. Hydrolysis and decarboxylation then yields a methyl ketone. Even simple alkanoic acids can be converted into methyl or trifluoromethyl ketones this way. This side reaction may be prevented by avoiding a large excess of acetic anhydride. When aromatic aldehydes are condensed with a succinic anhydride, lactones are sometimes the main product. As discussed in my carbon dioxide videos, carboxylic acids with a leaving group in beta position decarboxylate readily. This was also the case in this example. Thus, such condensation decarboxylation sequences enable the conversion of aromatic aldehydes into unsaturated acids with 3 more carbon atoms. Amides are weak carbon acids only and require either strong bases or high reaction temperatures to add to aldehydes. In this example, dimethylacetamide was both solvent and nucleophile, and as base potassium phosphate was used. Despite the high temperature, the reaction still required almost 3 days to attain completion. More acidic than simple amides are imides. Here, a lactam was first trifluoroacetylated and then condensed with 4-fluorobenzaldehyde and potassium terzbutoxide. This condensation already proceeded in refluxing THF. Similarly unreactive as amides are nitriles. In this optimized procedure, propionitrile was condensed with an aldehyde in DMSO with potassium hydroxide as base. The starting aldehyde was enolizable but not very acidic, and apparently sufficiently stable under these reaction conditions. Even sodium methoxide in methanol can sometimes condense nitriles with aldehydes. With the enolizable cyclohexane carbaldehyde, however, the yield was low. In the previous and this example, Cannizzaro reaction was probably also occurring and consuming aldehyde and base. Nitroalkanes with a pKa and DMSO of about 17 are more acidic than most aldehydes, and metallated nitroalkanes are therefore weak nucleophiles only. Nevertheless, condensations of nitroalkanes with aldehydes often proceed cleanly and in high yield. No strong bases, but rather catalytic amounts of amines or ammonium carboxylates are the best catalysts for such reactions, like in the self-condensation of aldehydes. In this example, a small amount of piperidine and molecular sieves were used as catalysts, and the reaction was finished in only 30 minutes at room temperature. Alternatively, such condensations can also be conducted by azeotropic water removal, as in this instance. It should be kept in mind, though, that nitroalkanes can also react irreversibly with strong bases and nucleophiles to aldehydes or ketones in the so-called NEF reaction. Thus, higher yields can often be attained under milder conditions, as those on the previous slide. As discussed in the previous video of this playlist, alkyl sulfones can be metallated by strong bases and then alkylated by aldehydes. Depending on the structure of the starting materials, the initially formed secondary alcohols may be stable or may eliminate water spontaneously. In this example, the dehydration did not occur on its own, but required benzoylation of the alkoxide. So, what can go wrong? All the products of this presentation are electron-deficient alkenes that can react with various nucleophiles. The most problematic would be the enolized aldehyde or the starting nucleophile. A Michael addition of these nucleophiles to the newly formed alkene would yield stable new products irreversibly. This will usually only occur if an excess of nucleophile is used. If the alkene is, however, strongly electrophilic and sterically undemanding, as for instance formaldehyde condensation products or the example shown here, then Michael additions can compete with the condensation reaction. Here, the byproduct was probably formed by addition of acetaldehyde to the nitro-olefin. This here is an instance where the initial condensation product isomerized and then dimerized by Michael addition. Such reactions can only be avoided by optimizing the amount and type of base, the concentration, and by keeping the reaction time as short as possible. Also, alcohols or amines may add to the new electron-deficient alkene, as in this example. Sometimes the resulting products are more stable than expected. Then, as we already saw in some of the previous examples, the intermediate alcohols do sometimes not eliminate water readily, and an additional dehydration step may be required. Further potential side reactions include cleavage of ketones, decarboxylations, and the hydrolysis of various carboxylic acid derivatives. Here, for instance, the initially formed carboxylic acid cleanly decarboxylated, as acids with good leaving groups in beta position often do. If enolates are formed stoichiometrically with strong bases, highly enolized aldehydes may just protonate the nucleophile instead of forming a new carbon-carbon bond. Then, in the presence of strong bases or acids, aldehydes may disproportionate into esters or mixtures of acids and alcohols, in the so-called Tishenko and Cannizzaro reactions. On this and the next slide there are some more examples, but many more have been reported. You can also find this reference list in the description of this video. The next presentation is about some alternative strategies for alafinating aldehydes, namely their condensation with 1,1-dihaloalkanes, with polar organometallics, and the McMurray reaction. See you then.